Okay, good morning, everyone. Today we start the second major part of the course, which is predictive analytics. And most likely, it's the most useful part in terms of your final project, because you can get a good idea of how you can basically do your second and third deliverable. You don't have to do predictive analytics, but based on my experience, usually your project are made of your knowledge from second chapter. It doesn't seem to work. Unfortunately, my pointer. Okay, let me just do I have it. Okay, 3 assignments are coming up. Assignment 6, 7, 8. So, assignment 8 is the one that I made of your friend's question about color accessibility. So, but no worries, it's pretty straightforward. Also, your first project deliverable is February 19th. So you have almost 2-3 weeks for your first deliverable. Any questions about your assignments or projects or from the previous session? By the way, we get back to visual analytics at the end of the semester for 2 reasons. First of all, the most of it is Power BI. If I have time, I go over some advanced Tableau topics too. But also, so some we have issues with the Mac laptops, but Clark IT has promised that they will have in the Clark's lab. So based on the promise, we might say sooner or later you can do some Power BI thing in your lab. And also over your Microsoft toolset, which is when you log into your email. So let me show it to you. So on the left part, when you click, there is a Power BI section. You cannot see, so let me. Okay, so when you go over your email to the left, on the left side, there's the Power BI. Oh my God. Okay, so let me. Okay, now you you see. So on your Clark email address, go to the left side. There's like some dots here. When you click on it, there's a Power BI section. Based on what I've seen, it seems they are still developing. It's not as good as Power BI desktop, but there is a good amount of overlap from the Power BI desktop that you might see in the end of the semester. Okay, so please work on your assignments and deliverables. In case you have questions, just let me know. So this week, we start predictive analytics to go over some concepts and standards. So among the standards, you will know about CRISPR, CIMA, and KDD. And also from next session, we start working with KNIME. So KNIME is the analytical tool, helps you to do so many predictive analytics without even coding. So in case you're not a fan of Python or you never had them, with this software, with drag and drop, we can do something very similar to what you do in Python. So no worries if you never had such a course before. So let's look at this video. This video shows a very cool application of predictive analytics in IBM Watson. So basically, IBM Watson used artificial intelligence or predictive analytics in Jeopardy game. And I'm not sure if you heard of it. So even if you're from other countries, there is exactly similar game in almost every nation around the world. So let me just play this video for you. I think I should hear.
I remember that morning going to the lab, and I was thinking, this is it. This is the last Jeopardy game.
This is Jeopardy, the IBM Challenge.
Here we go. Brad, if you're ready, make your first choice.
Let's take alternate meanings for 200, Alex.
Four-letter word for a vantage point or a belief. Brad.
What is a view?
Yes.
After the first clue of the game, which Brad won, I had just this horrible feeling at that moment that he was as good as everyone said he was, and he was just going to run the whole board on us.
Watson.
What is shoe?
You are right.
We actually took the lead. We were ahead of them, but then we started getting some questions wrong.
Watson.
What is leg?
No, I'm sorry, I can't accept that.
What is 1920s?
No.
What is chic?
No, sorry. Brad.
What is class?
Class, you got it. Watson.
What is Sauron?
Sauron is right, and that puts you into a tie for the lead with Brad.
The Double Jeopardy round of the first game, I thought was phenomenal.
Watson went on a tear.
Watson.
Who is Franz Liszt?
You are right.
What is violin?
Good.
Who is the church lady?
Yes. Watson.
What is narcolepsy?
You are right, and with that, you move to $36,681.
The risk was, Ken gets a daily double, bets big, gets it right, he's going to be well ahead, and then with that kind of lead going into Final Jeopardy, if he bets enough, he could end up winning the match.
Ken.
What's a committee?
We got to find that last daily double. We got to find that last daily double.
It was a crucial moment in the game. There was still a daily double on the board, and it was starting to become pretty clear that it was in the legal ease category. Let's go to legal ease for 1,200.
Watson.
What is executor?
Right.
Same category, 1,600.
Answer, daily double.
That was the moment when I knew it's over.
The category is 19th century novelists.
What Watson wants to do then is preserve the lead, not take a big risk, especially with Final Jeopardy, because just like for humans, Final Jeopardy is hard for Watson.
Now we come to Watson, who is Bram Stoker, and the wager. Hello, 17,973, and a two-day total of 77,147.
I would have thought that technology like this was years away, but it's here now. I have the bruised ego to prove it.
My past Jeopardy experiences have been great, but they weren't really weighty with this kind of technological, philosophical importance. I think we saw something important today.
Didn't really think very much about the implications until later and say, wow, wait a second, this is history.
Of course, this whole project is not ultimately about playing Jeopardy. It's about doing research and deep analytics and a natural language understanding. This is about taking the technology and applying it to solve problems people really care about. We're just so excited about all the things we can do with this.
I had thought this is the end. We get there, we're done. And I'm realizing it's just the beginning.
So what's your takeaway from this video? Do you think computers could beat human or not? So you think yes. So is there anyone who think computers cannot beat human? Yeah, why?
There are certain aspects of cannot be that efficient from decision. Just suppose aspect of
Yeah, actually, this is a big discussion, and I think both of the answers could be right. So let's say, I get to your point, but let's say I'm just making an example. In one of my papers that we'll publish soon, so I tried to predict Bitcoin price. So what I did, I look at more than 196 variables. So just assume my data set had 196 variables and 2 or 3 years of data. Human cannot process it. So you cannot expect a human and like process like a very large data set. Going back to IBM Watson, yeah. So they did something like a natural language processing or text mining. So the computer went through so many textual documents and tried to predict the answer of a question. So definitely when the data is getting too much large, they can beat humans. But as your friend said, maybe something needs intuitions. Maybe computers are still behind us. But I already gave you too many assignments, so I don't want to give you new assignments. But even you can see so many famous people, celebrities, they believe eventually computers would beat us, like Elon Musk. I think one of his tweets, he mentioned that. But anyway, there is a discussion about it at least. Another takeaway is, so they had a data set for IBM Watson application. So it seems they processed the data, they ran some machine learning or artificial language models, and they try to predict the answer of a question or bet on some certain question. So it's basically you would do something similar. Even we will using 9, we will do some natural language processing, but at the end there's a data set. You need to probably clean the data, prepare the data, and then you run some algorithms trying to predict some certain situations. Okay, so later on, you might take so many courses in analytics and end up being a data scientist or data analyst. Basically, if you go in that branch, you need to know more about the details. You need to do so many hands-on experience of everything from data gathering, data processing. Even sometimes, if you work with very large data sets, maybe you need to have some knowledge about Hadoop ecosystem, how to handle those data sets, and being able to extract information. However, you might be your focus might be on marketing or management in general. So at least you need to translate the output of people who are data scientists. So for example, if they say this model has the accuracy of this, or if they show you some result, you should be able to read them, maybe translate them, and just implement their outcomes in your own domain. So it's not something that you can evade from it. Even if you go other majors, you need to at least have some general grasp on predictive analytics and being able to translate other people's work. So there is some definitions, but generally speaking, there is no biblical term. You can see in many report or textbook, usually data mining, machine learning, or artificial intelligence are synonym. So what they do, basically, they have some certain algorithms. As I said, they could call it data mining algorithm, machine learning algorithms, or artificial intelligence algorithms. They just process the data and extract information. So this is the general process. So the pattern of information that they report is either association, prediction, cluster, or some sequential or series-based outcomes. So these are some general algorithms that we even work with some of them. So linear regression, logistic regression, neural network, support vector, k-nearest neighbors, decision trees are among them, but there is much more than this. Except for linear regression, which one you ever heard of it, or You heard about it before. No, except for decision tree, yeah. What about neural network? No. So in this course, I don't go to details. So we don't open the hood of the algorithm. We don't go under the hood. So we just look at this algorithm as a module, and we just look at their outcomes. So for example, if we look for accuracy, which one has a higher accuracy? So no worries if you never heard of them. So you work with them as a black box or as a module that you just insert input and take some outputs. Okay, so linear regression, you and decision tree, you might heard of them in your statistics courses or some mathematics-based courses. So generally speaking, there is two types of algorithms, like statistical algorithms such as decision tree and linear regression. So they are derived from statistics and mathematics. So there is so many conditions that they need to follow. For example, your data should be normal, or there should be some certain linear regressions between input and outputs. So they were around for like hundreds of years, so people use them. But more recently, your data doesn't follow some statistical condition, like maybe they don't have normal distribution, they don't follow normal distribution, or the relationship is not linear. One of them is like text. So you may or may not know, just imagine how to apply linear regression over a document. But in the IBM Watson, it seems they had the algorithm that could handle text documents. So there is a certain limitations of a statistical or white box algorithms. So they cannot process some certain types of the data. For this reason, people invented some machine learning based algorithms. They are much more flexible and they don't have limitations of the statistical algorithms. Generally speaking, you can divide data mining or machine learning in two types of algorithms: supervised versus unsupervised. For example, if you know so let's say you want to predict a Bitcoin price next day. So you have a dependent variable that you can predict. So we call it supervised. Because we know what we want to do. We know a certain dependent variable. But let's say you're a marketing company and you want to target some ads to some certain people. So here we don't have a dependent variable. We just want to find some people that have similar characteristics. And maybe we can divide people in some certain groups and just target different types of ads for them. In this case, you don't have a dependent variable to predict. You just basically, you want to find some clusters of people that have similarities, and then maybe you can consider different marketing campaigns based on their similarities. This is the general taxonomy of data mining. So interchangeably, sometimes I say AI algorithms or machine learning algorithms or data mining algorithms, all of them are the same. So from prediction part, we have some hands-on experience on classification and regression. From association, we will have market basket analysis. And from segmentation, we have some clustering. So basically, we cover all the types of data mining branches. If you look at the yellow part, or data mining algorithms, so we don't care which one is better, and you don't have to know them. So like, for example, you want to travel from Worcester to Boston. You might take BMW, you might take Honda, Tesla. So at the end, you want to go from an origin to a destination. So, but you don't know, maybe some of you have some mechanical knowledge, but at the end, you don't have to know what's the differences of BMW, Honda, or Tesla is very obvious, but you know, you don't have to know, but you want to reach a certain destination. Here, we have some measures. For example, we want to predict with higher accuracy. So, but we don't care which algorithm we use. As long as they produce a good amount of accuracy, we just use them. But it's actually a very good practice if you go under the hood of those algorithms. I think neural network should be very easy for you to understand. You might have a course that they taught you what does decision tree means. But frankly speaking, linear regression is the most difficult one. But you never went inside this. You just use it. So it just looks easy to you. But I used to teach that, and there is so many integral, and the proof of linear regression is really hard. So I think it takes like 1 page of like mathematical formula to just prove it. But you feel very comfortable with that because you have used it a lot. So, but what about visualization? So, and what is the key differences between visualizations and data mining statistics or machine learning AI algorithms? So, in visualization, usually you want to find a problem as quickly as possible. You have a very large data set that you want to make a quick decision, be very effective, or day-to-day decision making. So visualization is a really good thing. But at the end, your idea is very subjective. So you have some subjective tools that are very effective. In data mining, which we cover in this section, so we try to have more objective measures. We want to find some association. So we want to use some more objective measures to talk about maybe similar problems. So you might find a problem through visualization and use machine learning algorithms or data mining algorithms to find some correlations or some causal relationship that made that event. Any questions so far? So, and I don't see any question from people over Zoom. So these are the most common thing that I see non-professional people do. So for example, they don't know what kind of data they are working with. So they don't have any clue about the data. So they just see some columns. So you should understand what you're working with, especially for your project. So you need to know what does each variable means, not just dump them in the algorithm and just expect a miracle. So number of variables shouldn't be too low. Number of observations shouldn't be low. So there is some approaches. So even if your observations are very low, you can still use some different types of algorithms. But for your project, I don't recommend because it's a little more advanced level. And also, sometimes people don't do that much of data preparation. So if you see, let's say, actually it happened for me. So I was working with the transplantation data and I look at the people's weight. So it was for adult population and somebody's weight was less than 10 pounds. Do you think what could be a problem? Any guess?
So there could be a chance that there's probably more unidentified kids in there.
No, it's just for adults.
Just for adults? Less than 80 pounds?
10 pounds, less than. Yeah, it's not possible. Yeah. Yeah, it could be a typo. Just because it just the data was through manual entry, so maybe somebody just drop a 5 or 0. So, but if let's say less than 80 pounds, maybe it could be an outlier. So there's some approaches to handle them. Or sometimes you can derive new variables. Let's say you have a column of date, and basically, let's say your application is for marketing. So maybe you convert that date column to quarter column. So you write a quarter column, and under that column, maybe you put 1, 2, 3, 4. So based on the quarter that you're working with. Or you can make some dummy variables. So many times people who are not that much professional, they just forget to do data preparation. That sometimes even most of the, basically high proportion of your project time might be spent on data preparation. So if you use bad data, you shouldn't expect a miracle. So even you use the most advanced algorithms with the bad data, you would get some trash. So garbage in, garbage out. So having said that, each data mining project follows some certain or some column steps. So first part is understanding the data, then we go to over data preparation, algorithms, and maybe some implementation. And basically at the end, you have some information that you can use. So there is some general standards. So, but basically all of them are saying something similar. They just want you to have some certain steps for your project or data mining process. So for example, this is the CRISP-DM is the most famous one. It proposed in 1990 by a European consortium. So the second takeaway that you can get from this figure is the overall process is not one way. So sometimes maybe you do some business understanding, data gathering, preparation. And when you look at when you want to evaluate your model with this step, so you end up having a very low accuracy or any measure that you want to use. So maybe you think, okay, so it seems the model has a low accuracy. Maybe you can go one step here, change your model. Like here, you might use a decision tree. Maybe you change it to neural network, see what happens. Or maybe you go 2 steps. Maybe you focus more on data preparation, see if you have some outliers or some errors in your data to need to take care of. So basically, you might go back and forth a lot. Maybe in data preparation, you derive new variables, and just again, you just repeat it several times until you get a good performance. So the simplest one is accuracy. And when you are very confident about your model, maybe in the end or at the end, you just deploy your model. So it could be for marketing purposes, or basically if you want to do Bitcoin prediction, maybe you decide, should you buy or sell Bitcoin? So this is the deployment. So before deployment, it seems that you should have a good confidence about your model strength. You don't want, so if let's say my accuracy is 50%. So let's say I spend a lot of time, I made a model that can predict the price of Bitcoin with 50% chance. So do you use that model for trading? Some of your faces, it seems that you still use it, but anyone who don't want to use that model? So let me tell you the question again. So let's say I want to decide if I want to sell or Bitcoin today, because tomorrow it might go up or down. So what I do, So I look over the Bitcoin variables. So let me show to you. So for example, these are daily values. So open price, like max supply, volume, market cap. So first I read these variables to see what are they. So this is like business understanding. Then in data gathering, maybe I need to look over other prices, maybe oil. So I think for oil, I should go, okay, this. Maybe also oil price could affect it. Or large countries' currency might be also affected, but there is, let's say, rupees, there is more than 1 billion people use it. So maybe rupees and dollar exchange rate could also affect the Bitcoin price. Maybe I have a typo. So how to write rupees? This one? Yeah, I'm not sure is it right or not, but you see, even for rupees, I have like open price, volume, last price, those kind of things. So the first step here, I understand the Bitcoin variable, what those values in Bitcoin market means. I understand the relationship. Maybe I also gather data from different resources that could be effective. Then in data preparation, I look over if there is an outlier, or if there is a typo, or maybe I derive new variables. Like for example, I change day to month or 2 weeks. Then let's say here I'm using decision tree model, and here when I evaluate my prediction accuracy is 50% or 52%. Do you use this model for buying or selling Bitcoin today? So you said no. Is there anyone say yes? So why do you say no? Yeah, you are looking over the very low performance, like 50% almost. So it just means if I just toss a coin, so the accuracy of tossing a coin is 50% because it could be either head or tail. I spend a lot of time from here to here, and my accuracy is like just tossing a coin. So it seems either I made a mistake or that has a problem in the data. So I go back, maybe in the modeling, use different model, or maybe in data preparation, I derive new variables, or even maybe also I check if the Federal Reserve rate could affect, or maybe Dow Jones stock market index could be effective. So I maybe add those variables into my data set. Then I come here. So what about now 80%? Do you think you use it? Yeah, maybe 80% for some of you is good. For some of you still you don't trust. So, or you don't want to have 20% risk. So you just go back and forth. Maybe when you get 90%, you feel more confidence, or you feel, okay, 90% sounds like good accuracy rate. So now, let's say the model saying that with a 90% chance, tomorrow's Bitcoin price would jump. So maybe it's better to buy it today because your model is saying that tomorrow there's a race. Or it would say with 90%, tomorrow Bitcoin price goes down. So you just sell whatever Bitcoin that you have. Any question about Christian or these issues that people might face? Let me just go back. Yeah, but believe me or not, this is very common bad practices that I usually see every semester. Schema is another one. They use different terms like sampling, which just means data gathering, or exploring maybe means understanding your data or variables. Modifying could be data preparation. So still they use different terms, but at the end just means you do data gathering, data processing, using model, assessing your algorithm, and you just back and forth or do a cycle until you reach a good accuracy. This is another basically a standard KDD. Although the shape is different and the names could be a little different, but the overall process is exactly the same. It simply you start from a very base to the section that you get some good information, but also you need to just go back and forth until you reach a good performance. So this is a survey about the standards people use in their publications. QSTL is the most common one. Then somebody just use their own standard or own approach. Schema, KDD, these are the most famous. Okay, let's talk about classification versus, let's talk about regression versus clustering. So what is the goal of regression? What you do in regression? So I think I have a short here. So I think this is the easiest regression formula that you might have. Right? So what you do, you predict Y. So you have A and B are given and X is your input, you predict that. Clustering is like my previous example where you try to categorize your observations or your people or whatever data set you have to some certain groups that have the highest similarity. Okay, let's talk about, or let's compare simplex versus very complex models. So you might see in the Christian standard, I said you need maybe even for I talk about Bitcoin price. So I said maybe you need to get oil market price or rupees dollar exchange rate or maybe a stock market prices. So you can keep adding more variables. So, but there's a catch. When you just keep adding more variables, you make your model complex and more complex. So you might at the end you might get a very high accuracy for a sample data that you want to train your model. But the problem is when you just have too many variables, your model probably is you cannot generalize it for future. Let's see what I mean. So again, let me go to Bitcoin problem. So let's say I have a data set for 2 years of Bitcoin price. So, and in that 2 year, I just pick some part for training a machine learning algorithm. Then maybe for another part, I just want to see how good is my model. So on the board, let's say this is like 2 years worth of Bitcoin data. So I have some, let's say maybe one is volume, open price. So you name it, so many variables. And this is like each row is a date. For training my model, I pick this part. Just then run some advanced algorithms and train a good model. Then I test it here. Let's say my accuracy is 99%. But what happens, let's say I'm very satisfied with the model, but now I want to use it for next 10 days. So I want to use this 99% accurate model for the next 10 days. What happens, since my model is too complex, I cannot generalize it for future use. So maybe in next 10 days, accuracy might just drop to 60%. So this is the problem that happens when you have too much of variables for training your model, or when you have a very complex model. So your model would train very well on the data that is given, but you cannot generalize it for future use. So this figure is talking about that. It just said you should have good amount of variables. You shouldn't, if you have a very low amount of variables, probably you have underfitting. Too much of variables might be overfitting. So as you see in overfitting, this line almost catches most of the points. So this is good for current use, but probably you cannot use it for future. So you cannot generalize it. So it's better not to have too much complex models and not just too simplistic models, something in the middle. And this is actually very subjective still. There is some ways that you can find good number of variables that I teach you. So we call it variable selection. So in variable selection, we just pick the variables that have the highest accuracy, and we try to be very simplistic. Hopefully my papers come soon. So in that paper, you see that I used, I did data gathering over 192 variables for predicting the price of Bitcoin. But then I tried to have a more simplistic model, and then I just use 5 variables. So there is some ways that among those 192 variables, I just pick 5 of them because I want to have a more applicable, more generalizable model. So in your project, it's not good to have too much of variables. Again, I teach you later how to do that, how to reach from 192 to just 5 variables. Yeah, I think I just talked about training versus validating. So from the data set that you have, you divide your data set in 2 sections randomly. One section for training, another section for validating your model, and see if you are happy with the accuracy or not. What time is it? Yes, we have time, yeah. So these are some general measures that we consider about to see if you have a good model or not. One could be accuracy. Sometimes people call it hit rate. How fast or age is your model? Can you scalable it? Can you have some scale your model for larger data set, and also can you interpret your data, your model or not? The last part is very interesting. So you can interpret linear regression and decision tree. So if you had the course, what's the like neural network, SVM, those models are very good in predictions. They can handle many kinds of non-linear relationships, but they are not good for interpreting. So if you can have a statistical model such as decision tree or linear regression that you can interpret easily, we try to have them because we can easily see what happens for the prediction. But for neural network, SVM, they are not transparent models, they're black box. We just look at the outcomes. So if we can have decision tree with a very high accuracy, we prefer it in comparison with neural network, because we can see what happens inside the model, how decision tree decides tomorrow Bitcoin price goes up or down. So here, if you want to review decision tree, I put a video link here, but you don't have to in case you're interested. One of my friends talking about interpreting decision tree models in this video. So if you have time, please watch it later. Okay. So we talk about model evaluation. So if we want to see if we are confident about model's outcome, these are some general performance measures like accuracy, true positive rate, or sensitivity, true negative rate, or specificity, precision, and recall. So for each of those red numbers that you see, they're just some examples. For example, if true positive count is 50 and like false positive count is 60 and so on and so forth for remaining, what could be your accuracy? What could be your sensitivity, specificity, and recall? So at the end, we want to have a high accuracy and having high true positive rate and high true negative rate. So they are not necessary to are named positive and negative. So again, I go to good old example of Bitcoin. So for Bitcoin, true positive rate, positive could be price going up, negative could be going down. So let's say I have a model with the accuracy of 95%, true positive rate or sensitivity of 98%, true negative or specificity of 48%. So maybe if you set accuracy, you would be very happy to use it. 95% sounds good. True positive is still even better, but true negative rate is R. So true negative is 48%. So what does it mean? So if when price goes down, my model even worse than just tossing a coin. So in this case, you don't prefer to use your model. There is some certain reason why you see such outcomes. One reason, maybe you just go back here to the data set. Maybe in my data set, most of the days price goes up, and just a few days price goes down. So when this is my data set, let's say 85% of time my price goes up, 50% it goes down. Since most of my data sets for up days, my model will be trained much better for up days than down days. There is some methods that you can handle this issue, but actually here there is so much of biased model. So you might, this is not the only reason, but this is actually one of the reasons. Sometimes you see the artificial intelligence or AI models are very bad for female or people of colors. It's not the only reason, but let's say we want to have a model to just assign a credit line. And 85% of them are white men, and 50%, or just say men. 50% are women. So what happens here, you already have a data set is just vast majority of about the men. So you expect your model can predict a good credit line. So let's say you end up working like Chase. Actually, one of your alumni, her name is Chrissy. I think she hired at Chase. So let's say you end up being in Chase and you have and you made a survey or you look at previous customers, and your data set, almost all of them are men and just few of them female. So maybe your model won't, in that bank, your model won't go well when you want to assign a credit line for the female customer. Or same could be for people of color. So let's say if your vast majority of data set is for white men, let's say 2% are like Asian women or Black women. So your model might be very biased towards those groups. Again, this is a very important part in data preparation. So, especially if you don't want to have a bad reputation or get sued in the data preparation part, you should take care of this. Or when you want to do prediction, you do prediction for different people and see how good is your model for predicting them. If you see such a red flags, maybe you need to go back to see what was the reason for having such a biased model. So in the next video, actually it happened for Apple credit card, and I just played in the next session. So there's actually happened for a couple who applied Apple credit card, and the man got, I think he got 10 times more than his wife. I think I already talked about this. So when you want to train a model, just keep, but you know, we will have some hands-on experiences, but before that, just see. So you have a part of your data that you train your model, and after you train, you need to test to see if you are satisfied with your model. And again, if you have any issues in the training data set, for the test, you might see the issues. One was vast difference between true positive rate and true negative rate. There is another performance measure, which people call it area under the AUC curve, or in short, AUC. Actually, could look very complex, but the good thing, AUC takes care of both positive rate and negative rate. So if you have a very high AUC, it just means you have a high true positive rate and true negative rate. So basically, AUC just summarizes true positive rate and true negative rate together. If your AUC is near 1, means it seems your model is very good, it's not biased to either negative or positives, or up and down, or female and male. And when you look at some papers, this is one of the most common performance measures. So near 0.5 means just tossing a coin. Near 1 means having a very good model that can have a high true positive and true negative rates. So any questions so far? So another concept is k-fold cross-validation. Looking back here, I said to check performance of your model, you divide your data in one train set and one test set. But let's say you want to have more confidence. What can you do? You try that train and test multiple times. So like here, I divide my data in 10 sections. So instead of just doing one train, one test each time, I pick 10% for test and the remaining 90% for training. So first, this is the first piece of the pie that I use it for test. Then in the next situation, I put it back into train and just take the second part of the pie for evaluating my model. And I just do it 10 times. So instead of one train and test, here you have 10 train, 10 test. So the outcome of here is much more reliable because it brings more confidence. So for example, for each pie, you don't want to see, you want to see high accuracy and also high true positive rate and true negative rate, which should be close to each other too. So also talk about your number of observations that should be high enough. But if you, for your project or any real case scenarios, if your observation is low, these are some methods that you can use, apply machine learning algorithm for low number of observations. And still you can use it if you want to challenge yourself. This is like, but you know, I can help you a little bit, but also you need to Google it to see how you can handle low amount of observations and having high and reliable accuracy. So these are the different, again, another sets of algorithms and classification techniques. But again, no worries if you've never heard of them. At the end, you just need to know you have one input, you have a module for model or classification models here, output. What you care to have a good input, and also your output should be reliable and high accuracy. I just want to go over if you have previous statistics course, you need to just read a little bit and review the concepts. It definitely helps you. For example, one of the issues is multicollinearity. So can anyone remember, or have you ever had this topic before? No? Okay. So let me just tell you just one example. Let's say, which actually happened to me. So my data set was about transplantation, and I wanted to see after heart transplantation, can a patient can live more than 1 year or not, or more than 1 month or not. They just help surgeons to have some second idea about should they give an organ to a patient or not. So you don't want to give an organ to a patient who dies in 1 week. Maybe there's other patient that you can save them, they can live 10 years. So again, at the end, we don't want to just force surgeons. We just want to give them some data-driven idea. So they are the person who make the final decision. But let me just talk about multicollinearity problem. So my dependent variable was either 1 or 0. So 1 means they survived 1 year. 0 means they don't survive. And I have two variables. One of them was BMI. Another was weight. So in this case, which you learn later, I've seen if a patient have a high BMI, they have a lower chance of survival, which makes sense, right? So if somebody is very obese and you do heart transplantation, they may die. So they may not survive 1 year. So maybe before transplantation, they should lose their weight to have a higher chance of survival. So fun fact, we see the weight. So if a patient has a higher weight, the coefficient shows, so because there's a plus or minus coefficients for each of them. So BMI had negative coefficient. If you have a higher BMI, less chance. For weight was positive. So sometimes it happens. So if there is a high association, and you know that BMI and weight have a very high association. So again, shouldn't worry too much, but in case you should consider for your report. So if you have two variables that are very highly correlated, your final model might mess up in their sign of their coefficient, which here doesn't make sense at all. More specifically for statistical models like linear regression, you see such a thing a lot. So if you want to have more intuitive models, you should consider them and maybe just use one of them, not two of them. Because if you show this model to a doctor, they just laugh at you and they may not trust you. So it seems your model is nonsense. So this happened in the reporting part. So just keep in machine learning algorithms that like neural network SVM, you usually don't see these issues, but in, let's say, in linear regression, it's very common. So if you see such a thing, so what happened actually, I had near 180 variables, and I used some algorithms to pick 10. And BMI and weight was among them. Because of high collinearity, or correlation between BMI and weight, the coefficient was stupid. So what I did, I went back to 180 variables, and here I just did 179. I exclude weight and just did the remaining. So as you see, you just go back and forth to have a better model. And it didn't change my accuracy. Accuracy was almost the same. But now if I show my model to somebody, they buy it. So it makes sense for them. Okay, last example about correlation versus causation. Just keep in mind, in this course, you work with the correlation. So we find some correlation between BMI and patient survival, but we don't prove it. We just see a high correlation between these two factors, and we just report it. So when you write your report, you shouldn't write in the way that you want to prove that one variable or some certain variables cause some certain outcomes. Look at this example. This makes a lot of sense when I play it for you.
Hello, I'm Paul Henney, and I'm a philosophy graduate student at Duke University. And in this video, I'm going to talk to you about correlation and causation. Maria and Andy are high school students in Arizona. Andy always gets an A on his math test when it's sunny outside. On one sunny day, before Andy goes to math class, he tells Maria, "I'm going to ace this test today because it's sunny." Maria objects. "No, Andy, you'll not ace this test because it's sunny. You'll ace this test because you studied. The fact that it's sunny outside has nothing to do with it." Andy responds, "But Maria, I always ace my tests when it's sunny." Maria replies, "Okay, sure, but that's just because you always study for your math tests, and it's always sunny here in Arizona. The sunniness does not cause you to ace the test." Maria's correct. Andy's making a mistake, right? The sunniness doesn't cause Andy to ace his test. The two events, the sunniness and Andy acing his test, occur together without one causing the other. In other words, the two events are correlated in some way, but there's no causal relation between them. Andy's reasoning here is fallacious. Simply because two events are correlated does not mean that one caused the other. This conflation of correlation and causation is what we will talk about in this video. First, let's consider some other examples. Fido barks when his tail wags. People with higher grades in college have higher grades in high school. People who take vitamin C recover more quickly from a cold. These are correlations. That is, there's a correspondence between these events. For example, the dog, Fido, barks when his tail wags. But there's no reason to suspect that there's a causal relation between these events. While these events often occur together, there are many times when Fido's tail wags and he doesn't bark, and there are times when Fido barks but doesn't wag his tail.
So just let's stop here. So when this puppy barks, you can predict if he or she would just, you see some movement in his tail, right? But you can predict the tail movement or shaking from bark, but it's not the cause of it. There is a correlation for prediction. But again, the variable that you try to, when you want to predict through correlation, your variable should make sense.
Furthermore, we may suspect that there is some common cause for these events, like Fido's excitement when his owner comes home. Now that we can agree that these are cases of correlation without causation, we can discuss two types of correlation, positive and negative. In the next video, we'll discuss how these types of correlation specifically relate to different types of causation. But for now, let's just introduce them. When events frequently occur together, like in the examples above, they are positively correlated. If two events are positively correlated, then when one event is present, the other is often present as well. In our first example, it being a sunny day in Arizona is positively correlated with Andy succeeding on his math test. On the other hand, two states are negatively correlated when it's likely that when one event occurs, the other will not occur. For instance, when it snows, it's often not very sunny, so snowing and sunniness are negatively correlated. We often hear about positive and negative correlations, especially in the news. Headlines like, "Taking vitamin C helps you recover more quickly from a cold," indicate positive correlations. Taking vitamin C is positively correlated with recovering from the common cold more quickly than if one had not taken vitamin C. Or headlines like, "Eating more nuts makes you less likely to have higher levels of bad cholesterol," indicates that eating more nuts is negatively correlated with having higher levels of bad cholesterol. You may have heard headlines like these and had conversations with some friends about them. And you may have heard someone say something like, "Awesome, so I'll just eat more nuts and get rid of my bad cholesterol." You may have also had the experience of someone else saying, "Yeah, but that's just correlation, not causation." Of course, this person may just be a jerk, but they are right to point this out. Unless you had evidence that a causal relation held, it is a mistake to suggest that this correlation is actually a causal relation. So it'd be wrong to say that eating more nuts will cause you to have lower levels of bad cholesterol, unless you had evidence that the causal relation held. So let's consider an example where two events are positively correlated when neither causes the other. Consider this again. People with higher grades in college have higher grades in high school. Here, earning higher grades in college is positively correlated with earning higher grades in high school. Now, it's incorrect, as we've discussed, to claim that earning high grades in high school always causes someone to earn high grades in college. Nonetheless, earning high grades in high school may sometimes cause a person to earn high grades in college. For example, Jane may have gotten good grades during high school, and some of those grades transferred to her college, which causes her success in college. Here, success in high school for Jane causes her success in college. But most of the time, it is not the success in high school that causes success in college. It is usually someone's working hard in college courses that causes that person to succeed in college. And at that type level of the statement, where we are identifying a correspondence of two data sets, the causal claim is false. So again, the two events, high school success and college success, are positively correlated, but they do not cause one another. When two events are correlated, it may seem that one causes the other, but there may be alternative explanations we've ignored, like working hard in college courses causes that person's overall success in college. So it's fallacious to conclude from only the fact that two states are positively or negatively correlated that one causes the other, because there may be another cause that explains the outcome. It may be that there's a common cause for both of the events, or that there's some alternative cause altogether. On the other hand, the correlation might just simply be a coincidence. But this explanation and other questions will have to wait for part 2, where we will talk more about the analysis of causation and
So actually, this video is mostly for you when you want to write your report. So the way that you write it, you should talk about some correlation and the correlation that you use for predicting, not causation. So there is another types of causal studies. So again, we don't cover it here, but if you have time, you can more than welcome study that and implement for your research. But the content that you learn in this class is for prediction through correlation. Okay, I think that's good for today. Let's just go over attendance. So this is the short link. Yeah, push.